Okay, so our next speaker is Tanayveer, and he's going to tell us about small-scale dynamos. Off you go.
All right. Hello, everyone. I'm Tanayveer, and as I mentioned, I'm a PhD student here at Max Planck Institute for Solar System Research. And my presentation would be on the effects of including the small-scale dynamo on stratification, convection, and intensity on simulations for uh, near-surface convection zone for Goldman sequence stars. All right. So the main motivation for studying this effect is uh, to see how quiet star magnetism can affect certain things. Why is this important? Uh, so quiet star magnetism is important for example, for determining the basal magnetic flux, which directly determines your chromospheric heating, which I would not be addressing here since, yeah, it will probably come later in my research. It could also conceivably affect the thermodynamic structure, which is the main focus of my talk over here. And as a result of that, it could also affect the intensity characteristics, histograms, central variations, line profiles, etc. I would briefly touch upon them, and these are actually topics for further research along our project. And the way to self-consistently include these in NHT simulations is to consider a field generated by a small-scale dynamo. Now, a small-scale dynamo, I'm sure all of you know over here, dynamo is basically a process where magnetic energy goes to a non-zero value at the limit time t approaches infinity relative to other time scales. The small scale part over here refers to the scale at which amplification in the field occurs. Theoretically, is essentially your kinetic plasma motions acting against, for example, a loop, stretching it, acting against the magnetic tension, folding it up and pushing it back. Okay, to the more interesting stuff. Methods. So Miriam Alsami introduced in his talk. It's a simulation code which solves for the conservative RMST equations in a 3D Cartesian box and allows us to simulate a section of the near surface convection zone and the atmosphere. It is realistic in the sense that it treats a lot of the detailed physics very well. Uh, the setup quickly is periodic in X and Y directions. The top boundary is very simple for magnetic fields. It's vertical only, and for the plasma, it's outflow only. At the bottom boundary, it's a stratified open boundary to allow for realistic looking convection to take place. And the entropy influx is specified in the bottom boundaries. So here we consider three stellar cases: an F3 star, a G2 star, a K0 star, and an M0 star. And these are uniquely specified by the surface gravity and the effective temperature. So these in range span gravity of 2000 for the S star, 2000 centimeter per second square for the F star to 6700 centimeter per second square for the N star, and an effective temperature of 6800 Kelvin to about 3800 Kelvin. So it covers a fair chunk of the main sequence HR diagram. I am considering only the solar metallicities here. Veronica is considering the effects of different metallicities, and she'll talk about that stuff in her talk afterwards. Now, to allow for a proper comparison, the number of granules need to be similar in all the cases we are looking at, and the height of the box should have the same number of pressure scales there. So I essentially, for these simulations, I scaled the boxes accordingly. They all have similar resolution related to that scaling. And to actually get the SST cases, what we did was we ran some initial hydrodynamic cases. And for several hours, till convection was pretty much in equilibrium, dynamic equilibrium. And then we introduced a zero net flux field of negligible strength, about 10⁻⁵ course. And then we just ran it all the cases for several more hours till the field was saturated, and then for some more hours to allow for a decent range of time to do averaging over. Okay, now quickly to the results. Here you see three plots. These are the relative changes in density, temperature, and gas pressure, respectively, for the four cases. These plots are basically the changes in these horizontally averaged quantities relative to the hydrodynamic case. And the colors over here are the blue color refers to the S star, black one to the G star, the green one to the K star, and the red one to the N star. One thing that you will the x-axis is basically the number of pressure scale depths below the surface, 0 corresponding roughly to the surface. One thing you'll notice over here is that the GK and N star have pretty negligible deviations in density compared to an S star, which goes up to almost 2% decrease near the surface. There's a corresponding change in the gas pressure as well, and there's a slight increase in gas pressure for the G and K star as well. And for the temperature, there is a slight increase near the surface for all cases, except maybe N star. Now, these can actually be understood in terms of turbulent pressure contribution. Let me elaborate a bit further on that. When you look at the hydrostatic balance for any stellar convection zone, you expect it to roughly be satisfied. So your gas gradient, the gas pressure gradient plus rho g should be roughly equal to 0. Naively, if you just consider the gas pressure, which is what I'm doing in the first plot over here, you would expect it to be 0 more or less, but as you can see, it's not quite the case. So that tells us that we are probably missing something. That missing term is basically the turbulent pressure, which includes contribution from the Reynolds and the Maxwell stresses. Once you plug them in, you get this plot, which very well satisfies the hydrostatic balance condition right up to the surface where convection overturning takes place. That tells us that turbulent pressure is kind of important to take into account while looking at stratification, etc. Pretty much everything is then. The contribution of turbulent pressure, the fraction of turbulent pressure relative to the gas pressure is quite prominent for the S star. And the main difference that comes when one goes from the hydrodynamic case to the small scale dynamo case is a reduction in turbulent pressure, which primarily comes about by a reduction in your convective velocities due to strong magnetic fields near the bottom boundary. And this reduction actually reflects back into the density stratification, which is primarily related by the gradient of total pressure to the density simply from the hydrostatic balance condition. Okay. Now, going to magnetic field characteristics. Once you plug in small scale dynamo, you expect it to take away some of the energy from the plasma motions, and you expect accordingly a decrease in the kinetic energy. And you do see such a decrease for all cases. The decrease itself is somewhat similar for the GK and N cases, but it's actually a bit more pronounced for the F case, going almost up to 50% near the bottom boundary, which also accordingly implies that the magnetic energy to kinetic energy ratio is nearly in equipartition near the bottom boundary. Since we're looking at 3D simulations, another interesting thing to look at would be the ratio of horizontal RMS fields to vertical RMS fields. And here is a plot for that. Here you see for the GK and M star, the ratio, especially near the middle of the box, is fairly close to the value of √2, which indicates nearly isotropic. Of course, it can't be completely isotropic because you always have a preferred direction in terms of convective velocities, but it's still quite close. So yeah, but for the S star, that ratio is actually much lower, almost near 1. Going on to more, I guess, interesting stuff. Here is a snapshot for the bolometric intensity for the hydrodynamic cases in the first row for the S, G, K, and M respectively cases. In the bottom row, there's a snapshot for the volumetric intensity snapshots for the small scale dynamo cases. And in the bottom row is the corresponding vertical magnetic field at the tau equal to 1 surface for the cases. Here you can actually, just by looking at these snapshots, you can very qualitatively see some small but still apparent changes when one goes from a hydrodynamic case to another, to the small scale dynamo case. For example, if you look at the S star granulation, you can see that at smaller scales in the granule centers, it's quite bright and turbulent looking, but as soon as you put in small scale dynamo fields, you see it becomes much smoother, almost solar-like. In fact, for the G star, you start getting bright points which corresponds to concentrations of magnetic fields. And well, this is a known result, but it's nice to see that getting verified in my simulations as well. In the K star, you also start seeing bright points that are actually much more prominent than the other bright points, especially against the fuzzy background granulation. And yes, here also they correspond to concentrations of magnetic field in the intergranular lanes. You do get bright points in the M star case as well, but they're much less frequent compared to the other three cases. Most prominently, they appear in the K star, then G, then F, and then M. One could look at this stuff in a bit more quantitative fashion. If you look at the intensity histogram. So here I'm plotting the intensity histogram normalized by the standard deviation of the intensity. Now, the reason I'm doing this is because if I don't do that, what I get is something like this. So the contrast in the S star is much higher compared to an M star. It's almost high. It's almost 2 orders of magnitude higher. So it really becomes difficult to tell what's going on in terms of differences between the small scale dynamo and the hydrodynamic case. So taking care of that, here we can see small but significant looking differences in intensity histogram for all 4 cases compared to the hydrodynamic cases, which are represented by lighter colors, but for the same color scheme. There are mainly 3. Yeah, you would notice that all these histograms have a bimodal distribution, with the darker lobe corresponding to intergranular lanes, the brighter lobe corresponding to the granule centers, and the brighter tail over here corresponds to these bright features. Now, what we get for in terms of differences, we get a higher count for the intergranular lane features. That should not be brighter. That should be higher count. And in terms of granule centers, you get again a higher count for granule centers for the hydrodynamic cases. You also get more bright features for G and K stars, which I pointed out in terms of these bright points, but they are less for S and M stars. They are less for F stars in particular because most of the bright features in F stars for the hydrodynamic case came from the turbulent looking granule centers and not from, yeah. For G and K stars, these bright features are essentially magnetic bright points, as I mentioned. In terms of volumetric flux, there's a slight decrease for the F star to an order of about 0.5%, and there's a slight increase for the G and K star, but for the M star, it's pretty much unchanged. And that's basically my talk. To summarize, small scale dynamo fields in cool main sequence stellar photospheres essentially act by reduction of convective velocities. For S star, this reduction actually becomes fairly significant, and that ends up affecting the whole thermodynamic stratification to a couple of percent in terms of density, temperature, and pressure. All of these changes reflect in the intensity characteristics as well. You get a reduction in convective velocity, especially for the S star, and you get these bright magnetic point features which have the same mechanism as the G star bright points due to a hot wall effect from evacuated intergranular lanes, and this is most prominent for the K star. And you also get slight changes in total flux. For future outlook, so all of these simulations that I talked about just now, they are all gray atmosphere. So I am currently running, as you see, I am currently running non-gray simulations, which would take into account effect of different line profiles, different lines, spectral lines, and it would be, I think, interesting to look at the changes in convection in a bit more detail, look at the entropy profile, see how that changes and how to interpret those changes. And in terms of intensity, looking at the centrifugal invariation and spectral line asymmetries, that would be the next step in my project. And eventually to construct a finer grade over temperature and surface gravity for a small scale dynamo in cool main sequence for the space. Thank you.
Thank you very much for a great talk. I am just sitting, waiting for people to put their hands up. Just while they're doing that, can I ask you if your work has implications for the form of limb brightening or limb darkening laws that we use for other stars?
Sure. I mean, because when you include magnetic fields, you get in your intergranular lanes, they become evacuated. So if you start to look at them from the side, you tend to see more flux from the hotter parts of the stellar photosphere. So there will be changes. I mean, I can't say directly what exactly those changes would be, but you do expect there to be some changes. And this has been shown to be the case for the sun for similar MST simulations using miriam. So yeah, I do expect to see some changes at least.
And if the audience will forgive me, I have one other little question. On your slide where you had the panel of the surface brightnesses for the different stars, I noticed that the length scales were different for the different stars. If you had divided those length scales by the stellar radius, would all the, yes, this one, would all those patterns have looked the same? Would they all be the same size in terms of a stellar radius?
I actually haven't done that. It's a good question. I don't know really, but all of these patches are, I think, small enough that if you don't have an extremely fast rotating star, it wouldn't really matter as a function of radius. But yeah, I should probably check that as well at some point.
No, it'd be interesting to know.
Yeah.
I think we have to stop there and move on. Thank you very much, Tanayveer.